Hello, in this video I'll be explaining how we can use the 7-segment display on the FPGA board. Before I start, I'm going to explain how the 7-segment display works. Basically, from the name, we can tell that the 7-segment display consists of 7 different segments. Each of the segments represent an LED, and these LEDs are numbered from 0 to 6, where 0 is the least significant bit, and 6 is the highest significant bit. For us to display a number on the 7-segment display, we have to decide on which of the segments must be turned on. Additionally, for the DE2-70 board, we have an 8th LED called DP, which is short for decimal point. So in total, we have for the DE2-70 board 8 different bits which we need to provide values for. For other boards, there might be only 7 bits representing the segments of the 7-segment display without the decimal point. In the user manual, we're told that applying a low logic level to a segment causes it to light up. Meaning, if we want to turn on one of the segments from the 7-segment display, we need to give that bit a value of 0. So bit 0 here, if we want to turn it on, the value of that bit must be 0. So it's an active low signal. And vice versa, applying a high logic level will turn off the LED in that segment. To provide examples on this, here in the top we see a 7-segment display where all the segments are turned off, including the decimal point. Here we have a total of 8 bits, so the display output must be assigned a value of 8 bits of ones. If we want to display digit 1, meaning segment 1 and segment 2 must be turned on, then we're gonna assign the display vector values of ones, except for bit 1 and bit 2. We're gonna give them a value of 0 to turn on the LED at index 1 and 2. If we want to display digit 0, then all segments must be turned on except the 6th bit, so the segment number 6. And since we don't need the decimal point, in this case, the 8th bit, which is bit number 7, must also be given a value of 1. So bit 7, the highest significant bit, along with bit 6 for the segment in the middle, are given a value of 1 to turn them off, while all other segments are given a value of 0 to turn them on. Now for this to work, I already have a file named 7seg, which is a component or an entity that takes a 4-bit data input and outputs an 8-bit vector named display that will take care of the decoding part of the component. So 7seg component takes a 4-bit data, and then it decides on which bits of the display output must be on and which bits must be off. So here, when we want to display digit 0 on the 7-segment display, as we saw earlier, all bits must be turned on, so they're given a value of 0 except bit 6, which is the segment in the middle, and the decimal point. So in our code, we have a case statement that takes data and checks whether data is 0, 1, etc., and then it decides on the output display. Each of the 8 bits in display are given values based on the shape or the arrangement that we want to display on the 7-segment display. So this code is complete. It acts as a decoder for whenever we need to use the 7-segment display. To utilize this decoder 7-segment component on the counter circuit that I have already here, I'm gonna first look at the counter block diagram. My counter has 3 inputs: reset, enable, and mode, and it has one output of type vector that is 4-bit long. This is an up/down counter that is a BCD counter, so the output can range between 0 to 9, and it consists of only 4 bits. To utilize the 7-segment display, I'm gonna be connecting the output of my up-down counter to the input of the 7-segment display. So here I'll be creating a new file that uses 2 components in it, the up-down counter and the 7-segment display, where the inputs of this new file consist of the reset, the enable, the mode input, and the output is only the display, which is a vector containing 8 bits. In the middle, I will be needing a vector of type signal, a signal of type vector containing 4 bits. This vector will be using will be connecting the output of the counter to the input of data. This is going to be done in the port mapping part of the code. So back in Quartus, where I have the up-down counter that outputs the data stored in the vector y, and I also added the 7-segment decoder file. Now we're gonna create a new project. Now we're gonna create a new file by going to File, New. This file is also VHDL type, VHDL file. In it, I will add the library files. So import the library files, library IEEE, use work.all, use IEEE, that's standard logic. And then this entity is going to be my top level entity. I will call it counter is end. This counter and entity. This counter entity or component is gonna wrap or enclose in it 2 components, as we mentioned earlier, but it will still require me to have a reset input, enable mode, and it has one output called display that is 8 bits. So as ports, I'm gonna mention the reset, enable, and mode. These are still standard logic, so 1 bit. And I also need an output, let's say display, that is output of type vector. This is gonna be 7 down to 0. And if you're using a different type of FPGA board that does not have a decimal point, then in this case the display output will be only 6 down to 0, which is just 7 bits. We'll remove this bracket from here and close the ports bracket here. Now the last part of the code is going to be the architecture. I will call it maybe struct of counter is, I'm going to add an empty line before begin and then end architecture. Before begin, I will be declaring all the components that I need to use. I will be using the up-down counter and the 7-segment display. So I'll say component up-down counter end component. Before end component, I have to list all the ports of the up-down counter. So we're going to select the ports, including the semicolon at the end of the up-down counter, and paste them before the end component. I'll repeat the same for the 7-segment display. So I'm going to say component 7-seg, spell it correctly, make sure you spell it correctly, and then end component. I'm going to open the 7-segment display, select starting from the port until the closing bracket and the semicolon of the ports, copy, Control-C to copy, and then go back to the main file, the counter file, and paste the ports before the end component statement. The ports of the components must be copied exactly the way they are from in the original entity. So they're irrelevant to the names used in the counter ports. Now, looking into the block diagram, I can tell I will need one signal that is going to connect two components, the up-down counter and the 7-segment display. This signal currently does not have a name. I can call it either maybe Y or data or count. Let's say count, because it's going to hold the current count. And this signal is 4 bits, and all signals must be declared before begin. So I'll say signal count, and it's 4 bits. So standard logic vector. For 4 bits, we need to say 3 down to 0, semicolon. Now I will instantiate the up-down counter once. I'm going to call it UDC, up-down counter. UDC is an instance of the up-down counter, and then we need to say port map to port map the ports of the counter and the signals to the ports of the up-down counter based on the order used here or mentioned here. This counter requires reset port or input, enable, and then mode. So we'll have to follow the same order as the ports here, but the same names as the ports here and the signals here. So use the ports of the component for the order, but use the ports of the entity as well as the signals for the names. The reset is called reset. The enable is called enable as well. Mode is mode, but the output Y is going to be count. So we'll say count. And then I'm going to take or create a new instance of the 7-segment display. I'll call it SS for short, 7-segment. This is going to be an instance of the 7-segment, 7-seg. And we'll now do the port mapping. So port map. The 7-segment display takes only 2 ports. The first port is the data that we want to display, and then the second port is the 8-bit vector that is going to be the output of display. Again, use the order of the 7-segment display, but the names provided in the counter entity and or the signals. So the first port here, when we do the port mapping, is going to be the data, which I called count, and then the output, which is display. This is a port and output port. Then we're going to add a semicolon at the end. Before I compile, I'm going to save this file as the name of the entity, and then I will make it top level entity. So we're going to press Ctrl S to save the file, paste the counter name, the entity name. So I'm going to select this file, set it as top level entity, and then I'm going to click compile. Okay, we will check the errors by expanding the messages window, and then I'm going to double click on the first error message I see. I can see what's wrong. So we mentioned here standard logic. It should have been a vector because it's 7 down to 0. Standard logic vector. I can compile again until there are no more errors. Now, after successful compilation, we're gonna take care of the bin assignment. So we're gonna go to Assignments, Bin Planner, and then with the help of the user manual of the DE2-70 board, we're gonna find the locations needed for each of the ports. So I'll press Ctrl F here, and then we'll type hex to go to the display, and then hit enter until you see the table containing the location of hex 0. Hex 0 is the 7-segment display on the right of the FPGA board. So hex 0 will be mapped to display 0 port. So in here we're gonna set the location of display 0 as AE8. Display 0 will be AE8. Display 1 is AF9. Display 2 is AH9. And display 7 is our decimal point in the DE2-70 board. If you do not have the decimal point in your FPGA board, you can ignore display 7 or remove it completely from your code. So here display 7 will be mapped to the decimal point, so it's AF12. Now we're done with the locations needed for the 7-segment display. Lastly, we're going to add the locations needed for the rest of the design. I have an enable, a mode, and reset. Mode is going to control whether the counter is going to count up or down. So we want to use the switches for that, the toggle switches, so we can leave the toggle switch at the value 1 or 0 for a while as we increment or decrement the counter, as we enable the counter. For enable and reset, I'll be using the push buttons, so since they're active low, and the push button by default is 1, and when pressed is going to be providing a value of 0. So let's do the enable and reset first. The push buttons are called keys in the manual or in the FPGA board. So key 0 is the push button to the right of the FPGA board. This is going to be T29. I will use key 0 for the enable input. So T29 is our enable. And for reset, I will use the key right to the left of it. So it's push button 1, which is T28. T28. For the mode, as we said, we'll be using a switch. Switches are called SW, so it's SW0. I will use switch 0 for the mode. This is AA23. AA23. Once done, we can press Start I/O Analysis. Then I'm gonna click OK. Now in the bin planner window, go to File and select Export. To export the bin assignment file, we can now click Export and close the bin assignment window or the bin planner window. In Quartus, go to assignments, choose import assignments, and then now in Quartus, go to assignments and select import assignments. Click browse and find the bin assignment file. Click open, OK, and then compile once again. Now we'll click OK, and then go to the Tools menu, select Programmer, and ensure that the FPGA board is connected to the computer, and then select the USB blaster. Make sure to add the output file. If it's not added, you may add it by clicking on the Add File button and select the output folder, the output files folder, and select the SOF file. Next, click Start to start programming the FPGA board. So this is switch 0. Currently it's 0, meaning the mode is 0, so we'll be counting up. And this is key 0, which we used as the enable button. Key 1, we use it to reset. So the counter is currently in state A, so it's outputting 0. When we increment by pushing the key 0 button, we expect the counter to increment. So it should display 1, and then 2, 3, until it reaches 9. 9 after state 9 or state J. The next state should be state A, so the output should be 0. And it's working fine. We can now test the reset button. Reset is connected to key 1. So at any moment when key 1 is pressed, the next state will be state A, which will output 0. Now I'm going to make the mode input 1. So switch 0 will move it to the top, so it's going to be a decrementing counter. After state 0, the next state should be, after the output is 0, the next state should output 9. So if I press on key 0, the enable, I should see 9 and then 8, and it's a decrementing counter. At any moment, if mode is changed to 0, the counter should increment. And it's true. The counter is acting as expected.